Recording. Okay, recording. Go. Great. Fantastic. So, a couple of announcements. First, I got most of your homeworks into my mailbox, so thanks for doing that. And most of them actually look pretty nice. So, good job to those of you that were to kind of get a scanner or take good pictures with your phone, or whatever the case may be. So, thanks for doing that. The way I'm going to grade homework, I personally think that feedback's pretty important. So, the way I'm going to grade homework is usually I pick one problem, grade that one, and then check the rest for completion. So it's kind of a pain for me to try to go and print off a bunch of homeworks, then grade them by hand, then rescan them in and send them to everybody. So the way that I'm going to deal with this is if you do not receive feedback from me, that means that you got 100 on the homework. Okay. So will try to grade them quickly and post your grades to Blackboard. I try to get it done within 24 hours. I don't know how reasonable that is now with this whole restriction to certain devices and all that sort of stuff, but I'm going to try to grade them within 24 hours. If you do not hear anything back from me and you got 100 on your homework, there's not a lot of feedback that I'm going to give you anyway. I would give you your homework back with a 100 out of 100 on it. So good job. Okay, so instead of going through that rigmarole, if you got 100, I'm just not going to give you any sort of feedback. You already did a good job, so good job. If you do not get 100, then you should get some feedback from me, whether that's by email where I tell you, oh, you just had this one little thing wrong, or maybe I'll kind of print off your thing, correct it by hand with my red pen as normal, scan it in, and send it to you. Okay, so if you don't hear anything from me, got 100. If you didn't get 100, you should hear something from me about feedback. Okay, so that's how I'm going to deal with the homework. All right, continuing. Homework number 2 has been posted. It will be due for you guys on Thursday of next week, which is April 2nd. So it'll be due to my email inbox by 3 p.m. for you guys. It's only 3 problems. I'm not trying to overburden you guys, but I do got to make sure that you know how to do things like the multiple gear linkage analysis, and you can do relative acceleration analysis, which is what we're going to talk about over the next couple of lectures. Okay, so homework number 2 is posted. You can expect to see the solutions for homework number 1. I'll probably post those sometime tomorrow as well. So if you're studying for exam number 1 and you want to see what the solutions were because you weren't quite sure on something, those should be posted probably tomorrow. All right. Also, I posted some exam review problems. I think there's 5 of them or so to Blackboard. So if you need some additional practice problems, you want to go through those problems are kind of representative of what I would think could be on the exam. All right, so good things to check, good things to practice. And I'm always of the philosophy that I try to make the practice problems and the homeworks harder than the exam problems will be. All right, so if you know how to do the exam problems, you know how to do the practice problems, you know how to do the practice exam problems, you know how to do the homeworks, you're going to dominate. All right, you're going to crush the exam like a grape. Okay, you'll dominate. So that's that. We don't have a ton more material to cover before the exam, so we should probably be done with material by the end of lecture on Tuesday. Maybe we'll do some practice problems on Wednesday and Thursday, and then you should be ready to go for exam number 1. All right, so I'll give maybe 15 seconds or so here for any questions about what we got going on for the class into the chat. And if there's no questions, I'm going to proceed with the lecture. Okay, doesn't look like we have any questions here. And that's good. So let's go ahead and get started then. So today what I want to do is I want to sort of teach you guys a little shortcut for how you might quickly calculate velocity given a fixed axis rotation. Okay, so I'm going to motivate this shortcut by discussing a shortcut that you probably learned in statics to quickly calculate a moment. And then we'll talk about how the analogy in statics relates to what we've done so far in this mechanics class. Okay, so this dynamics, rigid body dynamics. Okay, so let's start with this. So we'll start with, this is of course not working. We'll start with a shortcut. for calculating velocity from fixed axis rotation. And I'm going to motivate this with an example. Specifically from statics. Okay. Are we supposed to see your whiteboard? Oh, shoot, I'm sorry. I forgot to share. Sharing is caring. All right, so here you guys should see the whiteboard. Sorry about that. Thanks for the note. So here we have a shortcut for calculating velocity from fixed axis rotation, and we're going to motivate this with an example from statics. So I'll give you guys a second to catch up. Sorry about not sharing there. This gives me time to hydrate. Perrier. All right. So here we're going to motivate with an example from statics. And that is a shortcut you should have learned in statics about how to calculate a moment quickly, given position and forces that are perpendicular from each other. Okay, so consider in statics, you might have a cantilevered beam that looks something like this. All right, so here's a cantilevered beam that's coming out of the wall. And let's say that this beam has a length which is 2.5 meters. Okay, sorry about the handwriting. Not my best. I'm working on the handwriting, I promise. And let's say that we apply force to the end of this particular beam, and let's give this force a magnitude. Let's say that it's 15 kilonewtons. All right, so let's put some points on here. Let's say that on the left-hand side, you've got a point A, and on the right-hand side over here, this is point B, right? So if we wanted to calculate what the moment of that force is about point B, we might want to calculate the moment about B, which is equal to R cross F, right? The position vector which arrives at A from B crossed with the force at A, if we, for instance, label this as the force at A here, which is 15 kilonewtons in J hat. Let's make this a little bit more clear. Force A, 15 kilonewtons pointing upwards, J hat. Okay, force, magnitude, and direction. All right. So you may have learned in your statics class that if R and F are perpendicular, you can quickly calculate the moment, because we know that if they're perpendicular, that the magnitude of the resulting moment is simply the magnitude of each one of the individual vectors multiplied together. All right, so magnitude is the magnitude of the moment MB is equal to the magnitude of the position vector RAB multiplied by the magnitude of the force at A. Or here for us, this is 2.5 meters multiplied by 15 kilonewtons. Okay, hopefully we're sort of like dusting this off and remembering what this is from statics. Here, the magnitude of the moment at B would be something like 37.5 kilonewton meters. So this is how you would figure out the relative magnitude. All right, now if you wanted the direction, you're going to start to employ that fancy right-hand rule that you probably learned about in this class for the first time, this statics class. All right, so direction is given by right-hand rule. So if we come back up to this particular piece, the way that we want to think about R cross F is I'm going to stick my arm from B to A. So I don't know if I got this right on camera, but I'll try my best. I'm going to reach out from B to A, and then I'm going to curl my fingers in the direction of the force, which here is up, and that will leave my thumb pointing into the whiteboard. All right. So here, the direction given by right-hand rule with this particular example is in negative k hat. All right. So if we crossed our position vector r with the force, we would get our thumb into the board, giving us this negative k hat. All right. So quickly, you could obtain here that the moment at B is the magnitude of the moment, which we know here is 37.5, just multiplying these two values together, kilonewton meters, and it's going to be in the negative k hat. All right. So that is something that you probably did in like week 7 of statics. And once you were taught that, you did it over and over and over and over and over. All right. So we want to make an analogy here between something like that, which you did in statics, with a cross product that we commonly see here in this class for rigid body dynamics, which is omega cross r. Okay. So the analogy in our class is typically we may want to calculate the velocity from fixed axis rotation, which might be something like the velocity is omega cross r. Okay, so the statics is r cross f. Here we have omega cross r. All right, so first we have to check. Actually, let's just look at an example. Actually, so let's look at example. And the example I'm going to take is the example that we did in class yesterday. So if I go to the PowerPoint slides and I pick off part of the example that we did in class yesterday with that sort of piston gear assembly, remember that we did the analysis of this particular gear. All right. And when we did, we first looked at the piece AB. And we looked at this. Okay, so I'm going to get rid of this picture and I'm just going to slide this guy over. And in this particular example, we wanted to start with the velocity of point B given the position vector that we have, which is r arriving at B from A, and the angular velocity vector omega AB. Okay, so our relative velocity equation was something like the velocity of B is equal to the velocity of A plus the angular velocity of our piece AB crossed with the position vector locating B from A. Told you, you're going to get sick of that equation. All right. Now we know in this particular example, since the gear is fixed here at A, that this velocity at A is 0, and we're simply left with the velocity of B is the angular velocity of the system AB crossed with the position vector locating B from A. All right. So this is the cross product that we want to execute. And now I want to make the analogy with what we did in statics. Okay, so remember in statics, we had something like r cross f. And with that particular analogy, we had to make sure that r and f were perpendicular to make sure that the system worked. All right, so back with our statics analogy, here is our sort of length or our position, and this is perpendicular to the force that was applied. Okay, so our shortcut here could work because r and f were perpendicular to each other. So let's make sure, or ask ourselves, are omega and r perpendicular to each other? If so, we can leverage the shortcut, and if not, we can't. So we need to sort of understand when these two things are perpendicular to each other. Fortunately for us, we are working entirely in the world of 2D planar dynamics. So what that means is when we're doing our analysis, and you've probably seen this now with your homework, is that anytime we have rotational velocity or rotational acceleration in the plane, the velocity vector omega is always pointing out of the plane. Okay? So omega is always out of plane for 2D analysis. Usually we write the velocity vector in k hat. Okay, so typically we'll be in k hat. Now the velocity vector is out of the plane, and typically when we do this analysis, our location, B locating A, or our position vector, B locating A, is always in the plane. It's on the page of the paper that we're working in. Okay, so R is always in the plane, usually I hat and j hat, or some combination thereof. So because of that, if our body is always rotating in the plane, that means the angular velocity vector is always out of the plane, and our position vector locating any points relative to other points in the plane will always be in that plane. That means that it is always the case in our class that the angular velocity vector omega is perpendicular to the position vector r. So for us, omega and r are always perpendicular. So we can always use this shortcut as long as we have planar motion. How are we doing? Kind of understand that concept? All right. So let's actually go through the analysis of the gear above, kind of using this idea of the shortcuts, and we'll sort of show how this works and how you might want to utilize it going forward. All right. So I'm gonna take this guy, copy him, and bring him down. So this is an example, and we're kind of running this example back, right? Last time we did sort of the full-blown brute force velocity analysis where we did full vector algebra and came up with a solution. That method is perfectly fine. Okay, if you want to go with that method and do that method and forget the shortcut that I'm about to teach you here, perfectly reasonable. Okay, actually, I prefer using the full-blown method myself. So when you see my solutions to exams, homeworks, so on and so forth, you'll see a full-blown solution. I'm not going to write like used shortcut here and show you the answer, right? I try to do the best I can showing you all the depth of the problem. Okay, but I want to show you at least sort of how you might want to think about going through these problems with the shortcut, because it in general might help you think about directionality of velocities given certain fixed axis rotations. All right, so we want the velocity of point B equal to the velocity of A plus the angular velocity of AB crossed with the position vector locating B from A. Right. So the way that we're going to enact this, we know that the velocity of A is 0. We want to find the magnitude of VB. Okay, well, that's easy. The magnitude of VB with our little shortcut is simply the magnitudes of the angular velocity vector AB multiplied by the magnitude of the position vector B locating A. All right. When we did this problem before, we converted the 2000 RPM of this particular crank into radians per second. And so the magnitude of the angular velocity vector we found to be 209 radians per second. And the magnitude of my position vector is pretty obvious. It's going to be this 3 inches here. So it's pretty trivial here to see then that the magnitude of the velocity of point B is 209 times 3, which in my head, 627 inches per second. Okay, so as Bon Jovi says, we're halfway there. All right, we've figured out the magnitude of this particular velocity, 627 inches per second. Now we need to enact the right-hand rule to sort of figure out the direction in which the velocity will act. So we're going to look at the direction with the right-hand rule. Okay, so our cross product generally is omega cross r. So the first thing we need to do is establish the direction of the vector omega. So if we look back at this picture, here's our angular velocity vector omega AB. We know that it's sort of rotating in the plane with this sort of clockwise motion, okay? So if I'm considering the direction of the vector of omega AB, when I curl my fingers in the direction of the motion, my thumb is going to be pointing into the page. So omega AB is in negative k hat, okay? So my thumb points into the page when I go through this angular velocity, all right? Next, I need to consider the direction of the position vector that locates B from A. So here we have a position vector that locates B from A, R, B, A. All right. So when I execute on this particular cross product, this is omega cross R, the way I'm going to execute is I'm going to stick my arm in the direction of the first portion of this, which is the angular velocity. So I'll stick my arm in the direction of the angular velocity, and I'll curl my fingers in the direction of the position RBA. When I do that, my thumb will stick in the direction that the velocity results. Here, my thumb should, if we do this properly, stick in the direction of VB. It's a little bit hard for me to like show it digitally or show it on camera, but maybe you guys can sort of give it a try by yourself. Kind of think about sticking your arm into the page and then curling your right hand fingers in the direction of RBA. Your thumb should be pointing in approximately the direction given by VB here. You should also know that because we're sort of following these specific rules, that the resultant velocity should be perpendicular to the position vector and the angular velocity vector as a result. Okay, so here this velocity vector is perpendicular to our position vector, which is true, and it is also perpendicular to the angular velocity vector, which is into the page. All right, so direction with the right-hand rule is going to be given by the vector that we showed above. All right, now we have to maybe put a unit vector to that particular location. So maybe I want to define a unit vector along this particular direction to help me define that direction mathematically. All right, so here I'll say that I need a unit vector that defines the velocity of B. All right, and here, after executing the right-hand rule and knowing that we have this perpendicular relationship, we have this angle that's sort of set up for us is 50 degrees. This will help me define the unit vector for this particular velocity. So here the unit vector is simply going to be cosine 50 degrees and I hat minus sine 50 degrees j hat. So this is the unit vector that defines this particular velocity after I sort of go through my right-hand rule, rigmarole, shenanigans, sugar me do, whatever you want to call it. Right? So finally, if we want to define the velocity itself, we'll say then that the velocity of B is equal to the magnitude of the velocity of B, which we found, multiplied by the unit vector that defines the velocity of B. So here This will be 627 inches per second multiplied by the unit vector cosine 50 degrees I hat minus sine 50 degrees j hat. Right. After going through this, distributing the 627 to the two different portions of the unit vector so that we can write this in rectangular components, you'll end up with the answer that we actually found previously for this, 403 I hat minus 480 j hat, and this is all inches per second. Right? So I made that a long discussion. It didn't really seem like a shortcut because I talked about this for 25 minutes, but 20 minutes, I guess. But it can help you, at a minimum, understand what the approximate velocity should be given some fixed axis rotation. So at a minimum, it should help you understand approximately which direction your velocity will end up going given a certain situation. And you might think about looking back at homework 1 for when that situation occurred, because you actually did see that situation in homework 1. So I'm going to pull up your homework 1 really quick, and let's look at this quickly. So you did have this sort of like gear crank sort of setup for problem number 5. And what you saw for this particular problem is that you had an angular velocity of this link BC, which was sort of acting with this fixed axis rotation about C. So in this particular example, your angular velocity vector is coming out of the page at you with positive K. And point B here is directed from point C in this perfectly horizontal direction. So if I want to enact my shortcut, I can simply calculate the velocity of point B directly by multiplying 75 millimeters times the magnitude of the angular velocity CB, which in this particular problem was 3 radians per second. So if I just multiply 75 by 3, I'll get 225. This is millimeters per second. And I can identify that my velocity will act perpendicular to this position vector, and following the right-hand rule will be acting downwards. Okay, so very quickly, without any vector analysis, I can simply say that, okay, if I just look at this guy, the velocity of point B is going to be 225 millimeters per second pointed down in J. All right, so you can still do the full-blown velocity analysis if you want. I got no problems with that. If you want to write it out fully and execute that way, perfectly fine. In fact, I actually prefer that. But if you want to sort of save yourself some time, or at least think about, does my answer make sense? You may want to consider some of this idea behind the right-hand rule and cross products and all this sort of good stuff. Okay. So how are we doing in the chat? Any questions so far? No questions in the chat. Are we awake out there? Do we need some jokes? Do we need a Rocky the dog interlude? Hell yeah jokes or hell yeah Rocky the dog? Okay. Some people want Rocky the dog. I think we got a minute. We can get Rocky in here. Hold on. Hi everyone, say hi to Rocky the dog. This is my dog Rocky. He's a little shaken up. I just pulled him from his slumber. Rocky the dog, Rocky the dog. Rawr. We can't see. Oh no. This is Rocky the dog. He's the best. Say hi, Rocky. Hi, Rocky. Okay. That's my quarantine buddy. We make quarantinis every night together. Can he do mechanics? He can run after a ball pretty fast. He understands that motion. Kind of. He doesn't really catch it in his mouth very well. He struggles. To be fair, I also struggle catching the tennis ball in my mouth. Okay. All right, continuing with the lecture. So here you should now see the PowerPoint slides relating to the topic I just had at hand, okay, which is how to calculate velocity quickly using this kind of shortcut idea, kind of highlighting the example that we just went over. All right, the next thing you'll notice on the notes is that there's some coverage here on instantaneous centers of rotation. So over the next 3 slides, there's a series of notes relating to this concept. All right. I'm actually going to forego the discussion of instantaneous centers of rotation in this particular class. The reason, a couple of reasons. First is the method of analysis for instantaneous centers of rotation is wrought with a lot of assumptions. And if you make an assumption about the situation and are incorrect, it's going to throw everything off. Okay. Secondly, I don't necessarily think that instantaneous centers or understanding the instantaneous center analysis saves you a lot of time. I think if you're good with vector analysis and good with cross products and all those sorts of things, then that methodology, which by the way always works, there's no real underlying assumptions there, will always work, is much more efficient and will work a lot better. Okay. So I have a series of slides here relating to instantaneous centers and how you could potentially use instantaneous centers to do your analysis, but I'm going to sort of forego the discussion. Okay. I'm never going to really ask you to utilize that methodology to solve a problem. You could always use the relative velocity equations, and those end up working just fine. Honestly, they end up working better. So it is a topic that kind of is discussed in the overarching view of the class, but because of the current situation, running out of time and all that sort of stuff, I'm choosing to forego instantaneous centers. And instead, we'll do a couple of, it'll give us more time to do some example problems next week. So I think generally people, we cover this quickly and they don't really use it anyway. So if you want to look at it, great. You want to use it, great. I understand it. If I see it on your homework or your exam, I'll get it. But I don't particularly think it's useful. And in fact, it can trip you up in a lot of situations. All right. Last thing of discussion today is moving forward on a discussion about acceleration analysis. So I'm going to switch back over to the whiteboard now and we'll go there for our analysis. Okay, so the next topic in this class will be acceleration analysis for general plane motion. Okay, so the acceleration analysis for general plane motion will proceed very similarly to the acceleration or the velocity analysis that we had for general plane motion. Okay, so we'll proceed similarly to velocity analysis. Namely that if we have 2 points on a rigid body, so here's our mechanics potato again, here's point A, here's point B, and this moves in space to some other location where it's now like rotated, and here is point A and here's point B. So it's rotated and translated and it has some completely new configuration. Then we can think of the acceleration analysis here, much like we think of the velocity analysis, where there is a translational and a fixed axis rotation component, and mathematically we just add them together to ultimately have the relationship between the accelerations of the 2 different points. So the acceleration, for instance, of point B is going to be the translational component, which is the acceleration of point A, which hopefully we know, plus the acceleration of point B relative to point A. Okay, so this is like your fixed axis acceleration components. So let's be clear about this. Here, this is like your translational component. And here, this is your fixed axis rotation component. All right. If you recall, what we did, I guess it wasn't last week. Yeah, we were all in quarantine last week. It was 2 weeks ago now. We derived the acceleration for a body in fixed axis rotation. So let's recall. For body with fixed axis rotation. And you did a little bit of this on homework number 1 with problems number 1 and 2. You had that the acceleration was equal to the angular acceleration alpha. Sorry, let me clean this up a little bit. Crossed with the position vector locating your point of interest, plus the angular velocity crossed with the velocity of that particular point. All right, so this was our general equation for fixed axis rotation. Or you might see this as alpha cross position vector r plus omega cross our velocity written in full form, which is omega cross r. All right, these are the two common forms of the acceleration of an object undergoing fixed axis rotation, right? So all we're going to do is take this equation here and plug it into the general equation for acceleration between two different points on a rigid body up there. So this is the fixed axis rotation component, and we're going to add the translational component to that. So finally, we end with the second of two equations, which you will write over and over and over and over in this class. That is, the acceleration of point B is equal to the acceleration of point A. This is the translational component of the acceleration, plus the fixed axis rotational acceleration component, which is the tangential portion, alpha, cross the position vector locating B from A. And this is alpha AB. If you want to be specific about it, this is the angular acceleration of the rigid body containing points A and B, plus the angular velocity of this object crossed with the angular velocity of this object crossed with the position vector locating B from A. All right, so this guy gets a box, this guy gets sparkles, this guy gets a special page in your notebook if you have a notebook, if you're even taking notes, if you're even awake. Sparkles! Okay, can you see that I'm slipping into madness here? It's a good thing we're not documenting this with a series of YouTube videos. Oh, wait. All right. So, reminder, if you're looking for the acceleration of some point B on an object, it's made up of the translational component of some other point on that body. Plus, here we have what we call the tangential acceleration component. And here, this is the centripetal or centrifugal acceleration. All right. I'll give you a second with that, and then I'm going to pull up some pictures on the PowerPoint slides to sort of show the differences between the translational acceleration, the fixed axis tangential component of acceleration, and the fixed axis centrifugal, centripetal, whatever you want to call it, portion of the acceleration. All right. I've foregone trying to draw some of this stuff on this pad because if I've already got the pictures in PowerPoint, let's just use those. All right. Sort of makes sense, right? Right. Rawr. All right. So let's take this away now and we'll share the PowerPoint slides. So here, this is a little bit more depth and showing some pictures about exactly what I'm talking about. So we just talked about deriving this angular acceleration, or sorry, the linear acceleration of point B is a combination of the tangential acceleration of A, plus here, this is the tangential acceleration coming from fixed axis rotation, and here is the centripetal portion coming from fixed axis rotation. All right, so pictorially, if we're interested in the acceleration of point B and given some acceleration of point A, this is a combination of both the translational component of the acceleration of point A, which we can see here represented at point B, plus the components that come from the fixed axis rotation of B about A. And we know that that fixed axis rotation, if A were fixed, would result in some tangential acceleration, which here is sort of indicated by this acceleration of B relative to A with the sub t, this tangential acceleration. And it also will have a normal component, the acceleration of B relative to A normal. This n is this sort of centripetal portion of the acceleration, always pointing inwards, right? We're always looking inwards, trying to make improvements. All right. So this is kind of where I'm going to stop today. I want to make sure that at the end of every lecture, I leave maybe 5 or so minutes for people to kind of hang out and ask questions and talk about if there's technical difficulties or whatever the case may be. So I'm going to cut it here today. We'll finish up these slides on Tuesday when we meet again, and we'll do an example problem where we're looking at calculating relative acceleration using this equation. So that'll be it for today for the lecture. I'll stick around and hang out if people want to ask questions or chat or whatever the case may be. Otherwise, thanks for coming. I hope you have a great weekend, and look for homework solutions and things like that for me to be posted in Blackboard pretty soon. Thanks. Yeah. Thanks, Jess. That was very nice. Very nice comment. Thank you. I hope it's at least entertaining watching me slip into madness. Slowly but surely, it's happening. Pretty soon, this will turn into something else.
Well, hey, it's almost 5 o'clock here, so.
Yeah, I guess that's true. 5 o'clock somewhere.
Exactly. Have a good weekend.
Yeah, see you later, Caleb. Money sign for the pupper. He's the best. I just kind of woke him up, so he wasn't in the best mood, but yeah, he's great.